So very good afternoon, everyone. It's our week 10 today. Welcome back to this problem solving session on the course control systems. So last week uh, you have learned, you have continued the discussion on body plot and also had an introduction to Nyquist plot, right? So in our session last week, what we did, we solved some problems on body plot, how to draw a body plot of a transfer function, and given a transfer function, how given a body plot, how you can like get a transfer function from that plot. So this is what we did in the last week. Today we will again solve some more problems based on body plot, more or less similar problems, so that that will give you more confidence uh, and will also help you solve some problems which are there in your assignment for this week. And we will also see how to draw a Nyquist plot. And in the next week, which is very, very important, we'll have Nyquist stability criteria, etc., and etc. Okay, so let's start today's session with this question. So the question says we have a body magnitude plot for a transfer function, which is given in the figure, and we have to find the steady state error corresponding to unit step, right? So if you recall, we have studied this in, I think, week 3 or week 4 when we studied second order systems, that steady state error, like for a type 0 system, is finite only when a unit step is applied, when a unit step input is applied. Similarly, for a ramp input, unit step. Similarly, for a type 1 system, steady state error is only finite if a ramp's input is applied. For a type 2 system, steady state error is only finite if a parabolic input is applied. Otherwise, for a ramp, for a type 1 system, if you apply unit step input, the steady state error is 0. And for a ramp input, for a type 1 system, if you apply a parabolic input, the steady state error is infinity. I hope this is very well clear to you, because we have already covered this, and we'll use the formula that we have seen in the earlier weeks before. But here the question is in terms of a body plot. So basically, we know the steady state error uh, depends on the type of the system, right? So the steady state error, it depends on the type of the system. What is the type of the system, right? And here we can find the transfer function from this plot, and that will give us the type of the system as well. And when we know the type of the system, we can easily find steady state error from the formula. So let me solve this question for you. So first of all, let's assume we have to find the transfer function from this body plot. So what did I say in the last lecture? We find the corner frequencies, and corner frequencies are the points where my slope changes. And if we can see from the plot, there is only one point where my slope is changing, and which is, I think, some omega. Let's assume which is omega. It's not given, it's omega, right? So I'm assuming at omega my frequency is changing. So then what will be my transfer function? So it is a, and okay, tell me what is the type of the system? What is the type of this system? See, I told you the type of the system is given by the number of poles at origin. So I'll write it again. This type of the system is given by number of poles at origin. And you already know that if you have, right? So you already know if you have a pole at origin, then your initial slope will be something like this, minus 20 dB per decade. So your initial slope will be something like this. Or if you have two poles at the origin, then your initial slope will be something like this, minus 40 dB per decade. If there is no initial slope, that means you have no pole at the origin. So when there is no pole, because since initial slope, is zero. Since initial slope is equal to zero, that means there is no pole or zero at the origin. So that means what? It's a type 0 system. There is no pole at the origin, so it means it's a type 0 system. And for a type 0 system, that's all you had to identify from this body plot as of now, that what is the type of the system, because we know for a type 0 system, the steady state error is given by A divided by 1 plus Kp. Right? So this is the formula for the steady state error of a type 0 system. Right? So this A is actually the magnitude of this step input. So it is the magnitude of step input, and here we have the step input is unit step. So it means my A is 1 here, and so A is 1 here, and this Kp I need to find. Right? And how will we find the Kp? This Kp, since we can write the transfer function in the time constant form, we can write this transfer function from the Bode plot like this: g of s k divided by 1 plus st, right? Because there is only one corner frequency here. So, which will be given by, which is omega, which is equal to 1 by t. So we can write this system in time constant form, because there is only one slope change, and which is a pole. Because see, if it is 0 dB per decade, and here we have minus 20 dB per decade. So there is a change from 0 dB to minus 20 dB. So it means there is a pole. So that's what I have written in the transfer function here. Right? Now, this K is equal to this Kp. When your system is in time constant form, this K is equal to Kp. So basically, you have to find K. That's it. So in all the questions that we do today, we will either find this steady. Whenever we are being asked to find the steady state error, basically you just have to find the K, right? This K. And in the last lecture, I told you this K is found from the initial slope. This K is found from the initial slope, right? So this formula, very, very important formula, that magnitude in decibels is given by minus 20 into R into log of omega naught. This will be plus or minus depending on whether there is a pole or a zero at the origin. So plus minus 20 into R into log of omega naught plus 20 log of K. Right? So this frequency, so now you can see here, see there, this R is this gives the number of poles at origin, where R, this we have discussed in the earlier class, in the last week. This R gives the number of poles or zeros at origin. So clearly we can see there is no pole or zero at the origin. It means my R is 0. So my magnitude in decibels will be equal to 20 log of K. This magnitude, initial magnitude, it's given. It's 40 decibels. So it's 40 decibels. My 40 is equal to 20 log of K. This 20 and 2, it means my log K is equal to 2. It means my K is equal to 10 to the power 2, which is equal to 100. So I got my K equal to be 100, and then I can easily find the steady state error, which is equal to 1 by 1 plus Kp, which is 100, which is equal to 1 divided by 101, it implies my steady state error. You can just solve it, and that's it. So this is the answer. Yeah, yeah. Please, Jayasuda, if you have any question, please ask. You were muted. Okay, so let's keep it as such. So I'll again repeat what is in this question, because you have some similar questions in your assignment. So basically, so you are given a Bode plot, Bode magnitude plot, and you are asked find the steady state error. The first thing you have to do to identify from this Bode plot is the type. So it's the type of the transfer function. So first of all, you should be able to find the transfer function from this Bode plot, or no need to find exact transfer function. At least you should get an idea what are the number of poles at the origin, which is basically given by this initial slope, So what is the initial slope that determines your type of the system? You see, there is no initial slope. Initial slope is constant. There is zero initial slope. It means there is no pole at the origin. If this initial slope would have been minus 20 dB per decade, then there would have been one pole at the origin. If this initial slope would have been plus 20 dB per decade, then there would have been 1 0 at the origin. If this initial slope would have been plus 40 dB per decade, then there would have been two zeros at the origin. And accordingly, my this formula will change. And accordingly, I'll get the value of K, right? So that's all you have to identify. You have to identify from the Bode plot, you have to identify the type, the transfer function basically. But if you're being asked to find the steady state error, then no need to find exact transfer function. Just see the initial slope that gives you the type of transfer function. From the type, you can find the value of K. And from the value of K, you can decide, you can get the steady state error. So now let's do another question, and that will give you more confidence. So again, similar question. You are given about a plot. You have to find. So I'll just make this Bode plot for you, and I would expect each one of you to answer this. So the Bode plot is like this. Wait, it is a different color. Wait. So this is the Bode plot, which is given. Again, no need to write, this is log of omega, and this is in decibels. Again, this is 40 decibels. Just to check your concept that I right now discussed, there is one slope change here, there is other slope change here, and you have to find the steady state error for the step input of 5u of t. So tell me, find the steady state error when a step input of 5 is applied to this transfer function whose Bode magnitude plot is shown in the figure. There is some omega 1, there is some omega 2, which I need not bother about. You only have to see what is the type of this transfer function, which is actually given by the initial slope, right? And using that, you can find the value of K. Yeah, everyone. We have right now solved this problem. You just don't have to do anything. Just some small change. Just some small change. Well, okay, let's solve it step by step. What is the type of the system? Can anybody tell me what's the type of the system? Type is given by, I'll give you a hint. Type is given by initial slope. Type is given by initial slope. If initial slope is 0, if initial slope is 0, then type is 0. If initial slope is minus 20 dB per decade, then you have one pole at the origin, then type is 1, etc., etc. If initial slope is, this type is given by the number of poles at origin. So if your initial slope is equal to minus 40 dB per decade, then your type is 2. Now tell me, what's the type? What's the type of this transfer function? And anyone? Anyone? What's the slope? What's the initial slope? What is initial slope? See, there is nothing given about what is the slope of this, what is the slope of this, because that is actually not needed. Jayasuda is not able to see the video. Is a problem with anybody else? Marwan or Shubham, are you able to see the video? Are you able to see my video? If there is no problem for you guys, then maybe Jayasuda, you can please like leave and join again. Maybe it's some network issue or something. Okay, you join again. Just leave the meeting and join it again. So okay. So see, okay, let me solve this question for you. See, the initial slope is 0. There is no initial slope. So the initial slope is 0. It means this is a type 0 system. You know it is a type 0 system. So why I'm telling you to identify the type? Because this type will enable you to see which formula you have to use, right? Because if it is a type 1 system, then you will use steady state error is equal to 1 by kV, right? If it's a type 0 system, steady state error is 1 divided by 1 plus kp, right? So on and so forth. So this type is important because it enables you to yeah. So now is the screen visible, Jayasuda? Is the screen visible to you? So the screen visible now? Oh, still not visible? I don't know. Maybe you can refresh or something. Or just wait a while. Wait a while. Maybe it will come as of on its own. Okay. So this is a type 0 system. It's a type 0 system because there is no initial slope. So that means your formula which you will use is steady state error is A divided by 1 plus Kp. This A you have to find and Kp you have to find. Now this Kp is actually the K which you will find from the Bode plot, right? So, and this A is actually the magnitude of the unit step, which is 5 here. So A is 5 here because it's given in the question, and Kp will be given by the initial slope. So again, I'll directly write this 40, which is the initial magnitude, is equal to 20 log of K. This and this goes, K is equal to 100 because we calculated it right away. Then it implies my steady state error is equal to 5 by 1 plus 100, which is equal to 5 by 101. Okay. Okay, so as simple as that. So basically what you have to do, you have to see initial slope for the type and then use the initial magnitude for the uh, K calculation. Now with that, please solve this question. I'm not marking X's because now already know because we have solved a lot of questions. Perfect. So this is my Bode plot. Again, this is in decibels. This is in log of omega. This is minus 20 dB per decade. This is also minus 20 dB per decade. And what you have to find the steady state error, find the steady state error for the given system if a unit step is applied. So for the steady state error, if unit step is applied. If unit step is applied, so please find the steady state error. Let me keep it as 40 decibels again for simplicity. Now tell me, anyone, Shubham or Marwan or Jazz Face, now my screen is visible to you. Very good. Marwan is saying 0. Can you explain, Marwan, why the 0? You can just unmute yourself and explain. I'm sorry, Jayasudha, I'm not able. I don't know why you're not able to say it. It's a type 1 system. Okay, it's a type. Of course, it's a type 1 system. Then why steady state error is 0? Marvin is saying it's steady state error is 0. So can you explain why? Okay, I think you got it. So the answer is basically it's a type 1 system and we're applying unit step. So for the steady state error to be finite for a type 1 system, the input has to be ramp, right? So the steady state error will only be finite for a type 1 system when we apply a ramp input. Otherwise, it will always be either 0 or infinity. So if you apply unit step, so then you have a 0 steady state error. If we apply parabolic input, then we have infinity. So is this clear? No need to write because yeah, I know you have got me. You've got me. This for this question, you got it right. Very good. So now, okay, with this, then let's solve this question. One more question. Okay, yes. So basically, you are given something like this. Okay, so your initial slope, yeah, this is given as minus 40 dB per decade. Okay, so and this is given as 0. No, let's see, not confuse. But what we are given is, carefully read the question, carefully see the question. Wait. Okay, so now it's much better. So what is given in the question is, so this point is given as 4 and this is given as 4/6. Yeah, let's not confuse with this. Yeah, this is given as 4. So, okay, so now what we have to find, and this is given as minus 40 dB per decibel, minus 40 dB per decade, and you have to the find the acceleration error coefficient. So we have to find the acceleration error coefficient. You have to find acceleration error coefficient here. So basically, even if you find the steady state error, that will be 1 by Ka. So this Ka you need to find. Later on, we can also find this Ka, and you assume that you are applying. You assume the steady state error is finite. That's why you have to find Ka. So assuming steady state error is finite, which is actually the case, you can see from the initial magnitude. So find the acceleration error coefficient Ka. So how you can find from this question, how you can find it? This is a very good question. So nothing is given, like whatever we have been doing, we were saying initial magnitude, but initial magnitude is not given, but something else is given. Make use of this dashed line, make use of this dashed line, like apply your brain and see what can we do with this dashed line. So again, here the slope is minus 40 dB per decade because I'm just extending this 40 dB per decade line. So first of all, you should know the system is of type 2. Why? Because there are two poles at the origin, which is confirmed from minus 40 dB initial slope. Minus 40 dB initial slope. Jayasudha is still able to see the screen. If possible, if you are still not able to see the screen, you can please try. Oh, great, great. That's a great thing. So you're able to see the screen. So now then please, like everybody, try to solve this question. It's a very easy question. What you have to do, you have to find the acceleration error coefficient. So when I'm asking you find acceleration error coefficient, it means obviously the slope is obviously the slope, obviously this acceleration, this steady state error is finite. Then and only acceleration error coefficient will come. And that is also confirmed from the initial slope, which is minus 40 dB per decade. That means there are two poles at the origin. There are two poles at the origin. So, but that was not required in this question because I already told you that in the question. Now, the question is how you will find this Ka, the acceleration error coefficient, which is actually K here, right? Okay, let me solve this. I'll just make use of this dashed line in the question. See, what I told you, this magnitude is given by plus or minus 20 into r log of omega plus 20 log of k. If you see this point, at this point, this is frequency, right? This is frequency. So at 4, my magnitude is 0. My magnitude is 0. So it's 0 dB when it is 4. And we know the slope is minus 40 dB. It means my R is 2, the type that there are two poles at the origin. So my slope is 0 when it is minus 20 into 2, but this is log of 4 plus 20 log of k. So if you solve it, it will be 40 log of 4 divided by 21.10 10 to the power answer. Yeah. So it will basically be like this. So 20 log of k is equal to 22 or 40 log of 4. This and this goes. So log of k is equal to twice log of 4. So which is equal to log of 4, which is equal to 1.204. And k is equal to 10 to the power 1.204, means my k is equal to 10 to the power answer, k is equal to 16. So k, basically k is equal to ka is equal to 16. That is the answer. So what you did, what I did, yeah, very good. So Marvin had solved it for 16. So what I did, I just made use of this slope thing which was given in the question, right? So if that is clear, now you should be able to solve this question. Everyone. So now we'll do 3 questions and you will tell me the answer. So we'll go step by step. Again, tell me this question. What's the, oh, sorry. You should be able to tell me answer quickly. Quickly. So this is 20. This is decibels. I don't care whatever this frequency is, but initial magnitude is 20, and you have to find quickly steady state error for step input. We have done it. Just a different value for initial magnitude. Yeah, everyone. So basically, you just have to find k. Number next question. In the meantime, what is k? What is Marwan? Is this steady state error or it's k? So my k will be k will be 10. Steady state error will be 1 by 10 plus 1, which is equal to 1 by 11. Okay, everybody, Shubham and Jayasudha, you are also able to solve it. Then solve this question. Yeah, now solve this question. This is given as 4, right? You have to find the steady state error for a ramp input. Find steady state error for a ramp input. Yeah, everybody, it's a good exercise. 0 decibels. Anything can be 10. You don't care. Yeah, this is minus 20 dB per decade. Solve this question and solve one more question. This will give you confidence. minus 40 dB per decade. Anything 20. Find steady state error for parabolic input. So I'm saying unit. Like the magnitude has to be unit for everything. So Radhifa join now. You're late today, and we have already solved some questions. So everyone, please solve this question. So what did you get the answer for this steady state error for rampant? 0.0625. Let me check. No, I think you have made some. What is the value of K that you got? Can you tell me, Marwan, what is the value of K that you got? Which question are you asking? Like this ramp input question? No, you will not get 16. You will not get 16. Okay, let me solve it. Radhifa, you also pay attention. So see, what we are basically doing for this question, the question in green color, let me do one thing. Let me do one thing. Oh, I don't know. Yeah, we can do one thing that can just move this page up. Yeah. So now see, everyone, see. The question is, for the body plot shown in this blue color, we have to find the steady state error for a ramp input. So first of all, while doing these questions, what you have to do, you should get an idea. You should get an idea of the type of the system. I don't know. No, 100 is also not correct. But don't worry. Don't worry. We'll solve it. Wait, Marvin. Let's solve it. Let's solve it. So see. Now see this for a ramp input. Since what is the type of this? What is the type of this system? What is the type? What is the type of this system? The type is 1. Why? Because if you see initial slope is minus 20 dB per decade, that means there is one pole at origin. That means the type is 1. The type is 1. Okay. Very good. So now you know for a type 1 system, when you apply a ramp input, steady state error is finite. Okay. So make sure you cross verify this. Otherwise, you will make mistake. So first of all, you have to identify whether steady state error will be finite or not. Otherwise, you can directly write 0 or infinity, right? So identify the type. After you found the type, so then you know for a steady state error, when you apply a ramp input for a type 1 system, when you apply a ramp input, steady state error is given by 1 divided by 1 by kV. Okay, so it means you have to find this kV. This kV is actually value of k that you will find. So you already know how do you find the value of k. You find the value of k from the initial magnitude, right? So you have the magnitude formula, which is magnitude in decibels is given by minus or plus or minus 20R into log of omega naught, or omega at which we are calculating this magnitude, plus 20 log of k. Now see, this magnitude, now see, okay, what we will do, we will make use of this point. We will make use of this point because initial magnitude is not given. So when at this frequency, when my frequency is 4, my slope here is minus 20 dB per decade. It means there is one pole at the origin. It means my R is 1. R is 1. So my 0 is equal to, there is a pole, so I'll use negative sign, 20 into 1 into log of 4 plus 20 log of k. That's it. Okay, so now let's solve it. This 20 and 20 will go. You will have log of k is equal to log of 4, right? So when you solve it, you will get k is equal to 4. When you solve it, you will get k is equal to 4. So it means your steady state error is equal to 1 by 4. Now, I don't know where you were making mistake, that why the 16 was coming and why this 0.01, I don't know. So I hope you have understood the problem. Now, similarly, please everybody try to solve this question. Again, similar question. So you have to find the steady state error for this system for a parabolic input. So you know steady state error will only be finite for a parabolic input if the type is 2. Okay, if the type is 2. Then what is the magnitude formula? Just make use of this point. Everybody please solve it, and I want answers. So put omega equal to 5 and magnitude is 0, because at 5 my magnitude is 0, and initials it's a pole, so the sign will be minus. It will be minus 20. Minus 20, it's a type 2 system. R will be 2. Minus 20 into 2 log of 5 plus log 20 log k is equal to 0. And then solve and tell me what is the answer. 25, very good. So Marwan found it. K is 25 and the steady state error is 1 by 25. So let me solve it. It will be something like this. Minus 20 into 2 log of 5 plus 20 log of k is equal to 0. And when you solve it, you will get k equal to 25. I hope you're able to solve log questions or logarithms, and at the same time also should be able to use calculator. And then my steady state error is equal to 1 by 25. So make sure sometimes you solve it correctly, but mark the wrong answer, because you will be asked steady state error, but in the question, uh, you will be also given the options of k. So make sure you don't make any mistakes. So before we end the Bode plot discussion, I would want everybody to solve this question, which is basically about finding transfer function from the Bode plot. So if you're able to solve it, then you have understood what is Bode plot and how you uh, like how you get transfer function from a Bode plot. And if you're able to solve this question, I think you'll be able to solve any question based on Bode plot. So now let's solve this question. Everybody please do it, because last week whoever has attended, I think he or she should be able to solve it. So initial slope is minus 40. Then there is minus 20. There's again minus 40. Oh, let me do one thing. Let me draw it in another color. So initial slope is this. There is this. Then there is this. Okay, so this is in decibels. Again, you know these things. This is log of omega. Now you have to locate corner frequencies. You have to locate corner frequencies. So there are 2 corner frequencies, right? And this point is 1. This is a very interesting question. And this slope is 20 dB. This slope is minus 20 dB. This slope, sorry, this is magnitude, minus 40 dB per decade. This is 20 degree minus 20 dB per decade. This is also minus 40 dB per decade. Okay, so let me mark this as omega 1, this as omega 2. So there are basically two corner frequencies. Corner frequencies are the points where my slope changes. So there are two corner frequencies. One is omega 1, other one is omega 2. So now try to formulate the transfer function. Try to formulate the transfer function. See, everybody solve it. I'll wait 2 minutes. Or if anybody has an idea how to solve this question, he or she can unmute and speak. Anyway, okay, let's go step by step. First, tell me what is the number of poles at origin? What are the number of poles at origin? Number of poles at origin. That is given by initial slope. So I told you number of poles. So obviously there is a pole. So 2. Very good. Jayasudha said 2. So I know there are 2 poles at the origin. So I know my transfer function will be something like this. K divided by S square. This I know. So it will be K divided by S square at the least because there are 2 poles at the origin. Now we have to see corner frequencies. So initially it's 40 dB per decade. Then there is a slope change at this point, which is omega 1, and it's from minus 40 to minus 20. So it means here, what do we have? What do we have here? We have a 0. Great. So we have a 0 because the slope is changing from minus 40 to minus 20. And at this point, the slope is changing from minus 20 to minus 40. It means we have a pole. So at 2 corner frequencies, we have 1 pole and we have 1 0. Okay, so can I write it like this? 1 plus S by omega 1 divided by 1 plus S by omega 2. Because at omega 1, I have a 0. At omega 2, I have a pole, right? So that's it. So this will be the structure of my transfer function. So this is the structure of my transfer function. But how you will get exact transfer function? For that, what do you need? You need to find K, and you know how to find K. K can be found from initial slope, or you can use formula. Second thing, what you have to find is omega 1 and omega 2. So we need to find omega 1, omega 2, and K, and that's it. That's it, right? So now see from the Bore plot. So see, how we can find this omega 1 is from the slope, from the slope. So if you see, you know this point, this is 1. And what's log of 1? What's log of 1? 0. Okay, so can we make use of this part? So see, this is minus 20 dB per decade. So can I write minus 20 is the slope. Okay, I'll write the formula first for slope. What is the formula for slope? Y2 minus Y1 divided by X2 minus X1 is equal to slope. So now see this triangle here. See this thing. Okay. See, I will assume this is my slope. Slope is minus 20 dB per decade, and my omega, my x1 is sorry. Let's assume this is my x2, and I know x2, which is 20. I know my x1, sorry, y1, which is 0. So see, this magnitude I know is 20. This magnitude I know is 0. This frequency I know is 1. This frequency I have to evaluate. Very simple, right? So what I will write, my y2 is 20 minus my y1 is 0. This is magnitude. My x2 is log of omega 1 minus my this x1, which is log of 1. See, this is log of 1, this is log of omega 1. So at y2, my frequency is omega 1. So I just wrote this slope formula, and this is equal to minus 20. Very good. So now let's solve it. Very simple. You know log 1 is 0, so you can easily find your omega 1 as 0.1. Done. So your omega 1 is 0.1. Now similarly, apply this formula here. You know the slope is again minus 20. So again, similarly, my minus 20 is equal to minus 20 minus 0 log of omega 2 minus log of 1. If you solve it, you will get omega 2 as 10. Very simple. I just use the slope formula now here. You see you have minus 20 now here. Fine. So you got omega 2 as 10. Very good. So you got omega 2 as 10. It doesn't matter, Shubham, it doesn't matter. So just make sure, see, just make sure you are applying this formula correctly. So y2 minus y1 in the denominator, it should be x2 minus x1, or you can write the other way, y1 minus y, whatever. So you can keep this log 1 as x2 or log this 20 as x1, y1, it doesn't matter, right? The answer will be the same. Now, so what do we get? So we got omega 2 as 10, omega 1 as 0.1. So now this is done, this is done. Now k. Now anybody, please tell me what should be the value of k? What should be the value of k? Who will tell me? And how do we do it? How do we do it? How do we do it? It's very simple. See, at this point, my frequency is 0.1, like it's omega 1. Your magnitude is 20, and your slope is minus 40, right? So I can write my magnitude, which is 20, is equal to minus, sorry, the slope is 20. The slope is 20, and there is one pole at the origin. Or you can use any formula. You can just make use of this 1 point. So at this magnitude is 0. You can apply any formula. So whatever formula you apply, the answer will be. So you yourself try it. Whatever ways we discussed right now, the answer will be k equal to 0.1. So you can use any formula. You can use when your magnitude is 0, the slope is minus 20. There are two poles at the origin, and just solve it, and you'll get it. Then after this, you're done. You're done with the transfer function, because that's all you needed. That's all you needed. Okay, so this part was actually based on what we discussed in the last chapter, but you have pretty much a good account of questions like that are based again on this Bode plot in this week as well. So that's why I discussed some questions. Now, before we move on to Nyquist plot, it's very important to discuss something else that will make your life very easy, which is called polar plot. So I will discuss polar plot. Why? Because we will solve. I know you have not discussed polar plot, so I'll discuss it in detail. Why? Because this polar plot makes my life very easy. When I have to plot, see, this polar plot is very easy to draw, number one. Number two, I will make Nyquist plots based on this polar plot. That will be very easy. Now, see, what is polar plot? So, see, it comes from the word polar. So basically, you plot something in polar coordinates. You plot something, and what is that something? I'll tell you. You plot something in polar coordinates. So, for example, you have a transfer function, g of s, gh of s, right? So you have this transfer function. What you do as of now, what we are doing things in frequency domain. So we will put s equal to j omega. So I'll get g of h j omega. Now it is a complex number because we have j here. So it is a complex number, and this complex number can be written as x plus jy, right? So this complex number can be written as x plus jy, or it can also be written as m e raised to the power j phi, right? So this means, see, if you have a complex number, how do you define a complex number? You define a complex number by its magnitude as well as the angle, right? We have discussed it in root locus as well. So basically, what you do in polar plot, we plot magnitude and phase of a transfer function in polar coordinate system. And in polar coordinate system, everything is in terms of phasors, right? So this is a phasor. So your complex number that has some magnitude as well as some angle, right? So that has some magnitude as well as some angle. So this magnitude m is equal to magnitude of GHJ omega, and this phi is the angle of GHJ omega. So basically, I'll just revise. You have a transfer function. You put s equal to j omega, you'll get a complex number, a transfer function in complex coordinates. That complex, see, this is Cartesian coordinate system. This is polar coordinate system. So in polar coordinate system, a complex number is represented by its magnitude as well as an angle, as well as a phase angle, right? So this m is magnitude and phi is angle. I have written it like this, right? And this m normally when we plot it, this gives the length of phasor, and this phi is the phase of phasor. I'll tell you in a minute what I mean. And if you see both these m and phase, both these m and phi, they are a function of omega. You see, they are a function of omega, right? And omega, what we do in frequency domain analysis, I told you, we vary omega from 0 to infinity, right? No, let's consider a scenario. Let's consider a scenario. Wait, I'll make it in a good way. Let's consider a scenario. What I told you as of now, what I told you in polar plot, we plot magnitude as well as phase of g omega, right? Gh, which is the transfer function. So this is my real part of gh. This is my imaginary part of gh in general. Or if you forget about this, see, if we are drawing a phasor, we have a complex number. I have a complex number. So this is this is my complex number. So this complex number will be represented in phasor form like this. You have its some magnitude, which is given by this length, and an angle. What is the angle which it is making? So this is my m, and this is my phi, and this is my complex number. Let's assume this is for my frequency omega equal to 0. It's for some frequency. I vary frequency. Now I got another, I got this magnitude and this phase. So let's assume this is omega equal to 10. So I'm varying frequency and I'm plotting magnitude and phase of a transfer function, right? Because in polar coordinates, of course, in polar coordinates, this length is given by the magnitude is given by the length of the phasor, and this angle is given by obviously the angle. Now see, I make another, I change frequency, uh, right? And I got this plot. Let's assume I got this plot. This is for another value. Let's assume I have omega equal to 100. And let's assume I got this for omega equal to 1000, right? Right. So what I did for different values of omega, I plotted what I plotted the transfer function in a phasor form, like I plotted it. The locus of this, see, the locus of these plots, is the polar plot. So the locus of these plots is the polar plot. So basically, I had an open loop transfer function. What I did, I know that open loop transfer function is in the form of, I can write that in the form of a complex number. Then that complex number, has a magnitude as well as a phase, which we have discussed pretty well in the root locus class. And if I change frequency, we know that both of these phase as well as magnitude, they are a function of frequency. And if we change omega from 0 to infinity, we obtain a locus, which is called a polar plot, So you might have not discussed it. The professor has probably directly discussed Nyquist plot, but your life will be very easy if you first understand this polar plot, because drawing a polar plot is very easy. From the polar plot, we can easily draw a Nyquist plot. See how. First of all, again, let me recall. So if I have this complex plane, I have actually explained it in detail, but not every one of you did attend all the lectures. So if it is real part, this is imaginary part. You know this, if I take angle as clockwise, that will be taken as negative. If the angle is taken as counterclockwise, that will be taken as positive. So I can make it like this. So this will be positive angle. This will be negative angle. Let me do one thing. Let me make it in a larger part. This is important, and this is very important for, yeah. So see, this is counterclockwise. So counterclockwise, I'll take positive angle. This I'll take negative angle clockwise. This is real part. This is imaginary part. Now, if I have to take angle. So this is my 0 degree. This is my 0 degree. This is my 90 degree. This is my 180 degree. This is my 270 degree. Right? And this is my, wait, I'll do one thing. This is my 0 degree. This is my 360 degree. Okay. Now, this is when I'm going clockwise, counterclockwise. This is when I'm going counterclockwise. I'm getting positive angle. But if I'm going clockwise, then this 270 is also minus 90. Then this 180 is also minus 180. Then this plus 90 is also minus 270. Then this 0 degree is also minus 360. This is very important. Make sure you remember this from now onwards, because while drawing a polar plot, this will come handy, and as well as in root locus as well. Now let's move forward. Let's do one question. So remember what we have to do. We have to vary frequency from 0 to infinity and plot phase as well as the angle, right? So see, if my GH of S is given as 1 divided by 1 plus ST, this is the transfer function that is given. Now solution. First of all, what you do, you put j omega, GH j omega, which is equal to 1 divided by 1 plus j omega t. Perfect. Now, got it. Now we have to find the magnitude as well as the angle, right? So what is the magnitude? What is the magnitude of this? The magnitude of this is given by 1 divided by under root of 1 square plus omega square t square. This is the magnitude. Very simple. Magnitude of any complex number, x plus iy. How do you write it? X under root of x square plus y square, right? And what is the phase? What is the phase of GHJ omega? I have also explained it when we were doing root locus, whoever has attended it. So the the phase for the numerator is 0 and for the denominator minus, then what is tan inverse of omega t by 1.
Omega by
So
1.
very good. So I hope you know how to write phase and how to write magnitude. Done. So if now we are done. So what we have to do now? Now see what we have to do. We have to vary frequency omega from 0 to infinity and find the magnitude of GHJ omega and the phase of GHJ omega. Right? Now see, when my omega is 0, see here, when your omega is 0, what is the magnitude? The magnitude is 1. The magnitude is 1. And what is the angle? What is the angle? The angle is 0. Tan inverse of when is, so yeah, tan inverse of 0 is 0, right? So now see, I'll make a polar plot as well. Wait. Please pay attention. This is very important. Very good. So see, this is my real part. This is my imaginary part. Now let's plot this. So for omega equal to 0, you have magnitude as 1 and angle as 0. So see, this is 0 degree here. So it will be something like this. Right? So it will be something like this. My magnitude is 1. So my magnitude is 1 and angle is 0. So it's 1 angle 0. So for omega equal to 0, this is for omega equal to 0. I got this thing. Now I will change it. Now let's put omega equal to let's put omega equal to 1 by t. Let's put omega equal to 1 by t. So when omega is 1 by t, see, when omega is 1 by t, so what it's what we'll get? So 1 by t square, this will vanish up. So you will get magnitude as 1 by root 2. Just put here for magnitude and for phase. And what will be the angle? Anybody? What will be the angle? Omega is 1 by t. T and t vanishes. Tan inverse of 1. Tan inverse of tan 45. So I'll get 45. But there is a minus sign. So I'll get minus 45 degree. Right? So now let me plot this. So for omega equal to 1 over t, I'll get something. I'll get magnitude is 1. See, initial magnitude was 1. Now next magnitude is root 2, 1 by root 2, which is 0.707, right? Which is 0.707. Now see, so I have something obviously less than 1 and angle is 45 degrees. So can I make it like this? So this is, let's assume my C. So this is when my omega is 1 over t, my angle is 0.707 angle minus 45 degree. Why minus 45? Because this way, if you go here, it will be minus, because this is minus 90 or plus 270. So minus angle will come clockwise, correct? Now put omega equal to infinity. Now put omega equal to infinity. So 1 by infinity, this magnitude is obviously 0. And what is the angle? Tan of, in where is tan infinity? 90 degrees. So minus 90 degree, right? So what is the magnitude? So it will be something. Now what is happening? Basically what is happening, initially your magnitude was 1, then the magnitude starts decreasing and decreasing and decreasing. So basically you will get something like here. So angle is this, so it will be a very small arrow of angle of length 0 and angle minus 90. So this point is 0 angle minus 90, right? Now what did I tell you at the last? What did I tell you? It is actually, polar plot is actually what? The locus of this, all the locus of this. It started from here, then as omega tends to infinity, it goes like this. It goes like this, correct? Now this is now, so see, so now we cannot do it like this for all the questions, then we will not be able to solve many questions on time. So what we do to draw it quickly, what we do, see what we do. We know when omega is 0, when omega is 0 and the magnitude is 1 and the angle is 0, so you got this point, you got this point, and when omega is infinity, magnitude is 0, angle is 90, so you got this point. So you can directly draw it like this. You can directly draw it like this. This arrow points it that it's going in this direction, that it's going in this direction. And this is called, the point where it starts is called tail of the polar plot. And the point where it converges or ends is called head. This is real part, this is imaginary part. So anybody has any doubt here? Because then and only we can move forwards. Anybody has any doubt? So no need to draw all those phasors. You can directly draw the direction in which the phasors are moving. Did you get it? Anybody has any doubt, please ask. You can directly unmute yourself. Okay, thank you, Shubham, for confirming it. If anybody has any doubt, please ask. Otherwise, it will be very difficult to follow up. So now quickly, let's move on. Let's move on. Quickly, let's move on, because we have to actually stop at Nyquist plot. So this is polar plot. Now let's do one more polar plot of this transfer function. 1 plus. So see, if you see it carefully, this is a type 0 first order system. This is type 0, but order is 1. This is type 0, but order is 1. And now what we are going to make this polar plot of a type 1 and order 2 system. Type 1 and order 2. Right? Now see, now first of all, what you have to do, solution, Gj omega, right? So I'll write directly, Gh omega is equal to 1 by j omega 1 plus j omega t. Now magnitude. So after this class, practice how you will write magnitude and phase angle, because I cannot waste time on writing this magnitude expressions for magnitude and phase angle. So this is very simple. We have done it. We have done it in the root locus. So the magnitude for this will be 1 by omega 1 plus omega square t square. That's what we did. What is the phase angle? GHJ omega. That is given by minus 90 degree minus tan inverse of omega t. Okay, see, for this question, I'll explain. Is there anyone who has doubt how we calculate this phase angle and magnitude? You can ask, don't hesitate. Just raise your hand. If you have any doubt, just raise your hand because this is very important how we write it. So then I can explain for this question and later on you can confirm or practice and then you'll be able. Okay, let me anyway explain how we write. See, for any complex number, x plus iy, how you write the magnitude, x square plus under root of x square plus y square. And obviously here you see magnitude of j omega is omega. Okay, so okay, fine. You know this. This is the expression that I got for magnitude and phase. Now let's vary omega and see what is my magnitude and what is my phase. When my omega is 0 and when my omega is infinity. So when my omega is 0, sorry, yeah. When my omega is 0, my magnitude is infinity and my phase is minus 90 degree. And when my omega is infinity, my magnitude is 0 and my phase is minus 180 degree. Now let's plot it. Okay, now let's plot it. See, when my omega is 0, my magnitude is infinity. So infinity in 90 minus 90 degree direction. So this in this direction, my magnitude is infinity. So we can only show infinity as a parallel line to that axis. So towards 90 degree, my magnitude is infinity. So whenever you have infinite magnitude, show it as a parallel line. So I'll show it like this. So it means it's coming from infinity. And as t tends to 0, as omega tends to infinity, my magnitude is going to 0, but in minus 180 degree direction. So it means I'll get something like this, right? So I'll get something like this. Let me make properly. Okay. So as omega tends to as omega tends to infinity, my magnitude is tending to 0 and angle is tending to minus 180, right? So this is the arrow. Very simple. See, this is 0 degree. This is minus 90 or plus 270. This is minus 180 or plus 180. It depends on how you are measuring it. Okay, so this is the polar plot of a type 1 and order 2 system, right? Type 1 and order 2 system. Now, what is the shortcut? What is the shortcut? Now, I'll tell you the shortcut. How to draw a polar plot in a very easy way. You just don't have to find magnitude and this angle again and again. So instead, what you have to do, so this is real, this is imaginary. You know these things. Now see, I'll use two colors. So tail is where, see, okay, Shubham is asking where is minus 180. See, this is 0 degree, this is 0 degree. If you go this way, it is plus 90 degree. If you go this way, it is minus 90 degree. If you go this way, it's plus 180 degree. If you go this way, it's minus 180 degree. That's how I have written it. So see, this is going, and finally it will be somewhere here, minus 180. Where's minus 180? Is it clear, Shubham? Okay, so okay. Okay, so now see, I'll use two colors. One is black. I'll write here, tail is black, which gives me the type and head is blue, which is given by order. Now see, I'll write here type, just give me a moment. I'll explain it. Type 0, type 1, type 2. This is a shortcut how you draw a polar plot. Type 3. Now see, order 1, order 2, order 3, order 4. Okay, now see, if you have a type 0 system, type 0 and order 1 system, you will start from here, your tail will start from here, and order is 1, so it will, I'll explain it in this, like here. So yeah, I'll explain it, explain it in a detail. Now see, if I have type 0, order 1, so my polar plot will start from here, and converge here. Okay, my polar plot will start here and converge here. That's what I said. Type 0, you start here and converge here. This is the direction of arrow. This is what we found here. So I had a type 0 and order 0 system, type 0 and order 1 system. You see, we got a polar plot of this form. That's what I made. Now, if I have a type 1 and order 2 system, if I have type 1 and order 2 system, then I'll get something like this. Type 1 and order 2. This will be I'll make it bigger. This will be my polar plot for a type 1 order 2 system. Now, if I have type 0 but order 2, then type 0 but order 2, then my Bode plot will start from here and converge here. So this is my type 0 and order 2. Now, anybody has any doubt here? Now, will you be able to draw all the polar plots without looking at the Wagner-Witten phase, only if you know the order and type? Is it clear, or should I explain it again? Should I explain it again for more types? Okay. Let me ask you. Let me ask you questions. You will tell me what is this Bode plot of which system? I have made this Bode plot which so there is this Bode plot. Now tell me what is the type and order. What is the type and order? This should be type 1. You see, type 1 and order 3. Type 1 and order 3. Okay, type 0, not type 0, it's type 1. Now tell me this polar plot. This polar plot. Now tell me one last. Tell me this. Yes, everybody can unmute and ask. Tell me, what's the
Type
type and
1,
order?
order 4.
Very good. Is type 1 and order 4. Now, I think you should be able to plot polar plots. Now, let's come to Nyquist plot. Why do we plot, why do we make polar plots, why do we make Nyquist plots? I think you have already gone through the lectures. If I even do that, then I don't think we will be able to solve any question, or like then it will take a lot of time and energy. So if you're coming to this question, what I'm assuming is that you already have gone through the lectures of the professor, and as well as also attempted the some of the assignment questions. And now, when we are discussing Nyquist plot, I will only tell you how we draw Nyquist plot. In the next lecture, maybe we can discuss Nyquist stability as well. But before we do that, you should. I'm assuming that you already know how you map, what is encirclement, what is enclosement, etc., and etc. Right? So I'm not going into the details of that. If you have not gone through those things now, it's very good time to study that, because your next two lectures, your next 2 weeks are very, very important from exam point of view, from gate point of view, from your class, or like your school, college exam point of view. They're very, very important, or any interview point of view. Your Nyquist plot and Nyquist stability criteria. We'll also discuss gain margin, phase margin as relative stability. And in the last week, we have lead lag compensator design. So that's very, very important. So that is actually the core of control system, right? Whenever somebody asks you control, or you have studied control, so they basically will ask you what is Nyquist, what is Bode plot, polar plot, gain margin, phase margin, lead lag compensator, etc. Rarely they'll ask you about stability, or they might ask, but whatever we have studied as of now, this forms the very, very important part of control, right? So now, how do we find, assuming again, you know what is Nyquist plot, it's the same, it's the polar plot. So how do you plot this thing? So you make a polar plot plus inverse polar plot. What is inverse polar plot? Inverse polar plot is the mirror image of polar plot. Okay, I'll write that later. So polar plot, inverse polar plot plus semicircle of infinite radius. Right? So semicircle of infinite radius, or how many semicircles, that is given by the type of the system. So if you have a type 1 semicircle, the type 1 system, so you will draw polar plot, inverse polar plot, and one semicircle of infinite radius. If you have type 2 system, you will draw polar plot, inverse polar plot, and two semicircles of infinite radius. If you have type 0 system, you'll draw polar plot and inverse polar plot. No need to draw semicircle of infinite radius. And what is this? What is this inverse polar plot? What is this inverse polar plot? Inverse polar plot is equal to mirror image of polar plot, mirror image of polar plot about real axis. About real axis. Now let's solve one question, and things will be very easy. Things will be very easy. This is what you have been asked in the assignment. See, let's assume you are given a transfer function, gh of s is given by 10 or anything, the numerator, and s plus 2 into s plus 4. Now, first of all, what we have to draw? We have to draw a polar plot, right? So let's draw a polar plot. The shape will be there will be a very nice shape. You'll see it. See, this is a real part. See, this is a real, this is imaginary. Now see, what is this? What is the type of the system? What's the order of the system? The system is of type 0 and order 2. The system is of type 0 and order 2. So my polar plot will come somewhere here. Right? So my polar plot will be something like this. Okay, so this is my polar plot. Done. We have studied this. See from here. Type 0 order 2. Type 0 order 2. So that's what it is. Type 0 order 2. So this is polar plot. Now we have to draw inverse polar plot because we are drawing Nyquist plot. So draw Nyquist plot. I'll just write draw the Nyquist plot. So for that, I draw the polar plot. Now I'll draw inverse polar plot. And what's inverse polar plot? The mirror image of polar plot across a real axis. And you also have to change the direction of arrow. So now see, this is the mirror image of polar plot across real axis. And see, this arrow direction also needs to be changed. So you have make sure you change the direction of arrow. Right? That's it. This is Nyquist plot of the given transfer function. Right? And see, I drew it. I did not mark what is this point, what is this point, like where is -1 plus j naught. That we will do in the next week when we discuss Nyquist stability. At least in this week, you should be able to draw the Nyquist plot. Okay, so this is Nyquist plot for this type 0 and order 2 transfer function. Now let's do for the same problem. Let's make it question. Let's make it a GHJ. Let's make it type 3. Sorry, let's make it type 1. So 10 divided by S into S plus 2 into S plus 4. Now my system is type 1 order 3. Now order 3. Let's draw the Bode plot. Let's draw the Nyquist plot. It's right here only. No, wait. Let's draw the Nyquist plot. So again, this is real and this is imaginary. So you have Nyquist plot we have to draw. You have the system type 1 order 3. Okay, so type 1 means it will start from here. It will start from here and end here. So you'll get something like this. Okay, this is your type 1 and order 3. You can always draw these polar plots based on what we discussed in the beginning, where you will find the magnitude of the transfer function, and then phase of the transfer function, put omega 0, put omega infinity, get exact values. Then you will get what is the value of this where it is intersecting this minus 80 or whatever. So you'll get everything. But here we just want to learn how to draw it, just the shape. Now we have to draw the inverse polar plot. Inverse is along the real axis. So inverse will be like this. Inverse will be like this. Right? So this is my inverse polar plot. Then what we have to do? Then we have to draw one infinite semicircle which is given by the type of the system, and you know the type of the system is 1, so we will draw one infinite semicircle. So then I will draw one infinite semicircle. So this is infinity. This radius is infinity. So this is the Nyquist plot for the given problem. Now, why I took it in this direction? Why I took it in this direction? This will be clear in your lectures. If you go through the lectures, the professor might discuss it that you're assuming the Nyquist contour in clockwise direction. So for this, you need to understand Nyquist contour, etc., etc. I'm not going into the details because that will need a lot of time. I'll need a lot of time in that. So I hope now, based on polar plot, you should be able to draw Nyquist plot. So drawing a polar plot is very easy, right? So that's very easy. And you can just find the magnitude as we did in the earlier questions. In this question, for example, we find the magnitude and then draw. And I explained it in detail, like you have to draw in terms of phasors, and the locus of that phasors is a polar plot. And after that, if you not want to do that, if you're just concerned with the shape, then just remember this table, this chart sort of. And from this chart, you can draw polar plot of most of the transfer functions, because you have some see, make sure you should know what is type and you should know what is order. See, when I say type of the transfer function, type is always given by open loop transfer function. But when I say order is given by the closed loop transfer function, the denominator of the closed loop transfer function. But how I was able, because in polar plot we see open loop transfer function, but how I was able to tell directly the order is 2 or the order is 3, because you see there is a constant term in the numerator. So see, my closed loop transfer function will be 1 plus gh equal to 0. That will again be the same thing. There will only be that thing in the denominator, right? So because that will be cancelled, whatever comes. So most of the problems that you will be able, and most of the problems that are asked in the questions, they fit in this chart. So if you know this chart, if you know how to draw this polar plot from this chart, you will be able to draw the Nyquist plot as well. Now, why we are making this polar plot? Why we are making Bode plot? Why we are making this Nyquist plot? There are some important questions which will mostly be answered in the next week. But make sure before you come to the next week, you watch all the lectures of the professor. You also attempt all the questions of the assignment, because next week is one of the most important, most toughest week of this course, right? So, and very, very important. I told you, Nyquist stability criteria. We will also check, we'll see relative stability. We'll see stability from Nyquist plot, stability from polar plot, stability from Bode plot, gain margin, phase margin from all these plots. That's going to be very, very important. And with this, I think you should be able to solve all the assignment questions. And also try, we have not solved many questions, so try to solve some previous year GATE problems. With that, you can get more confidence and then also solve the assignment problems, which are not that difficult. So if anybody has any question, please ask. Otherwise, we're good to stop here. Okay, so you don't have any question. I'm just stopping the recording. Thank you very much for joining this lecture.